Sorry for the late start. It's what happens when you get old. You forget things. Yeah, okay. So what we'll do today, I think we're just going to focus primarily on selection today. And I think I'm going to give you a little thought problem as I go through this, and then the work problem that I kind of do on the, I'm going to do a dominant selection model going through all those steps, and I'm going to give you a thought question. We'll do that, and then we'll finish up with the different kinds of selection. And at the end, what I'm going to present to you is a little table. I'm going to ask you to fill that in maybe. I suspect we won't be able to do it in the class, but kind of do that maybe to turn in next time or just to do it to help you understand. And the thing I'm really trying to focus on here are all these different kinds of selection. What you're looking at, there may be particular genes or alleles that are favorable, some are unfavored. And we're looking at the rate at which those favorable alleles get fixed within a population, that is, they go to 100%, and vice versa is the rate at which these bad or deleterious alleles get lost and go to 0%. And that's kind of what we're looking at, these various kinds of models and what the outcome is. So there are basic two outcomes. One is fixation, right, of a gene, a favorable gene, and loss of an unfavorable gene. We'll look at some other kinds of selection actually where you reach an equilibrium, where you don't lose them, and we'll be looking at what's called heterozygous advantage. And then we'll be looking at another important kind of selection called negative frequency dependent selection that actually maintain often both genes in a population at some equilibrium, and that's what we call a polymorphism as opposed to a monomorphism. Okay, so let's kind of go back a little bit to review before I jump into the work problem. Let's see. So if you remember here, we compared these two graphs, right? And this is what we're going to focus on. So when we look at A1 dominant, what we mean is both the homozygous and the heterozygote has the exact same fitness. They're both favored. They're set at 1. And there's a reduced fitness of the recessive homozygote, okay? And what you can see, here's the graph, and we'll come back to this. What you show is a rapid increase early on. So we're tracking the fate of a favorable allele when it's rare in a population. So for example, it might have arisen through mutation. And think back to that. Remember those agouti mutations for the melanistic genes in those mice? That would be an example of this. Anytime a mutation that's favorable originates, it goes from very low frequency potentially to a high frequency. Okay, so as we look at this, it goes really fast, then it plateaus off. In the other case of the incomplete dominance, where the heterozygote has an intermediate fitness between the dominant heterozygote and the homozygous recessive one, what you can see is it's slower in the initial phases, but it goes to fixation much faster. And do you remember how did we explain that? Why did this take longer to go to fixation? What happens when the favorable allele becomes common? Why is it so hard to get rid of? Yeah, because what you can see here, what happens is this unfavorable allele in the A2, right, is masked by that A1 allele. It has a fitness of 1. So the problem is selection can't, in general, see that. And when you start getting up to really high frequencies of a favorable gene, guess where A2 is mostly found in what kind of genotype? It's almost always found in the heterozygote. It's very hard as you start getting up towards, and you'll be doing this in lab, as you get up towards 100%, right? Most of the time that A2 allele is always going to be associated with the A1 allele, and it's going to be very rarely that you can get that homozygous A2 being produced through the basic processes of mating and Mendelian genetics. It's going to be a much lower frequency of getting this. So it's really hard to purge or remove deleterious genes from populations when you have this kind of selection. Is that true in this one? It's hard. You can see the A2 allele, when it's in the heterozygote, has a reduced fitness. So selection can kind of remove it. It's not hidden or masked, so it's easier to do. Okay. We're going to come back to this, but this is a little harder to wrap your brain around. So let's look at this example where the A1 is recessive. So let's look at it first. What in general is the favorable gene in this example? It's still the A1, right? Okay. So the A1 heterozygotes have the relative fitness set to 1. The other two have what? Reduced fitness. So they're about a 20% reduction in fitness compared to that homozygous. Why do we call it A1 recessive? That's what everybody, I know when you're sitting out there, you say, well, that can't be true. A1's always dominant. What we're talking about is A1 is recessive in terms of its effects on fitness, okay? And what you can see here is the fact that when A1 is with A2, it has a reduced fitness, and that's kind of considered a recessive effect. Okay. So let's just, we're not going to get bogged down too much in that, but let's look at the dynamics of that. Does that graph look a lot different than the other two? What do you notice here? This is the orange line right here. It's favorable. We're still looking P, small p is the frequency of the A1 allele. So we're saying this A1 recessive favorable allele arose at, through mutation. It's advantageous. But what happens, it takes a long time to increase in frequency. Why is that? So again, you kind of have to think back, when it's rare, what other gene is it going to be associated during that early phase? It's going to be all, think about it. If you got a bunch of individuals and there's a rare individual that has the mutation, the A1, and it mates with another individual, which thing is it mating with? The A2, right? That's all that's there. So it's going to produce mostly A2 offspring, but it's also going to produce some A1, offspring that have reduced fitness. So the problem here is if you have this sort of a favorable gene that's recessive, right, it goes through a long phase where it doesn't hardly increase at all. What happens as it gets to a point, though, when A1 is recessive, it takes much longer to increase in frequency, but once common, it goes to fixation quickly. And the reason is kind of the same thing, right, as before. Once it gets common, you're getting a lot of these genotypes, more of them, and it's highly favored, and it sweeps to fixation. It goes to fixation really quickly. But it goes through this extremely, look at this, 600 generations, and it's basically hovering around 0. Okay? Does that make sense? Okay. That's a little more difficult conceptually. Okay, let's go through the example, and I will show you maybe we'll do this. I don't see a cursor. Oh, there we go. Did you guys all watch the video tutorial? Okay, so we're going to go through this, and the example, the video tutorial I have on Moodle is exactly like this, but what I presented on Moodle was the case of indominant, right? That middle example. So what I'm going to show you is pretty much the same thing, pretty much the same starting numbers, but all we're going to do is change this to a dominant selection model so that one homozygote and the heterozygote have the exact same fitness. So let's kind of go through the phases of it. So the first thing we're going to have, the frequencies of the genotypes and alleles are exactly the same as in the thing I did in the video tutorial. There are 100 individuals, 80 are big A, 10 are heterozygous, and 10 are small a. Again, you need to be able to figure out how to figure out the allele frequencies from those genotype frequencies. And again, it's AA plus half of AA gives you the small a, gives you the frequency of the big A allele. So that's 0.8 plus half of 0.1 gives you A equal to 0.85, and A is 0.15. You can do the calculation, 0.1 times 0.5 times 0.1 will give you 0.15, but you don't have to. Okay. So those are the starting frequencies of the genotypes and alleles, and then we imagine some sort of selection event where something causes mortality of these genotypes. And the genotypes differ in terms of their survivorship during some sort of event. And it could be predation, it could be an environmental effect, it could be all sorts of things that could cause that selection that we've talked about. So what we're imagining here is the AA. Here are the number of individuals that survived that selection event, 45 and 2. So what do we do next? You want to determine the frequencies of those genotypes after selection, right, compared to where they started. Okay? So how do you do that? How do you do AA, big A? You had 40 to start with. How many? Yep. Okay. So this is what we call the relative survivorship. We often use a thing called lambda, if my thing would work. Okay? That's just what we call survivorship. Okay? What's the other one? What are the others? Yep. So 5 divided by 10 equals 0.5, and 2 divided by 10 equals 0.2. So what's different about this example from the previous model that was on the video tutorial? All the genotypes are, these two genotypes survivorship is exactly the same, right? 0.5 and 0.2. But in this case, what I'm showing you, the heterozygote has the survivorship that's the same, right? 50% of them survived, although there are fewer of them. 5 out of 10 survived. 50% survived for both the big A and the big A, and the heterozygote. So that's what differs. So this would be the case. Now we can determine fitness from this, right? How do we do that? Yeah, by the maximum survivorship value in that table, in the step above. So again, what we always do is relative fitness is always scaled, and it's always the highest value is set at 1. So the easiest way to do that, of course, is to just divide by that maximum survival rate. Okay? So we divide by 0.5 for each one of those to get the relative fitness. So this is the measure of their relative fitness and their relative survivorship compared to all other genotypes in the population. What do we get for big A, big A? 1. What do we get for this one? 1. And what do we get for that other one? 0.2 divided by 0.5, what's that equal to? You do need a calculator? No, come on. 0.4. Okay. Okay. So those are the relative fitnesses. So this is a case of dominant selection. The homozygous and the heterozygote have the exact same fitness. The small a has a reduced fitness in that. So what are the S values? You don't usually use those, but S is 1 minus W. No selection, and 0.6. Okay? That S is just 1 minus W. And that tells you the magnitude or the strength of selection, in this case, acting against the homozygous recessive, the small a. So it has that's actually pretty strong selection. Now what do we want to do? We'll go to C, which is calculating the normalized genotype frequencies after selection, okay? And I'm not going to fill in all the details and all the things that are on the table. You can see that from the thing, and I think I gave you a hard copy too of how to calculate these allele frequencies, okay? So basically what we do is we take the frequency before selection times the fitness is how you calculate these normalized genotype frequencies. So let's do AA, heterozygote, and that. Okay, so the original starting frequency before the selection event, right, was 0.8. And then you take it times its relative fitness, which is 1, okay? The relative frequency of the heterozygote was 0.1, and its relative fitness, in this case under dominant selection, is 1. And then the frequency of the homozygote was 0.1 times 0.4, okay? Those then give you values of 0.8. Did I do that right? Yeah, okay. 0.1 and 0.04. Okay. So what you want to do, you don't have to worry about that. You just sum all those things up, and that's what's called the mean fitness of the population. You add those up, and that's 0.92. The problem is this is just kind of mathematical. This is sort of mathematical keeping, so you can get the frequencies to sum up to 1. So this is just a kind of an inconvenient thing we all have to do to get these frequencies to sum up to 1, because you can see they don't sum up to 1 at that point. They sum up to 0.92. So basically all we have to do is figure out the frequency after selection. And what we're trying to get the genotypes, the frequencies to sum up to 1. And so basically all we do is we take each one of those values and divide by this 0.92. So we take 0.8 divided by 0.92, we take 0.1 divided by 0.92, and we take 0.04 divided by 0.92. These should hopefully all sum up to 1. And after you do those calculations, what do you get? Here's the frequency after selection of the big A is 0.87. Yeah, go to 3 digits just to be safe. This is 0.087, and this is 0.043. And those should sum up to 1. Okay? Yes? Why isn't it 0.94? Because it's point. Oh, it is. Oh, yeah, you're good. Oh, yeah. I was looking at the old one. Thank you. Erase, error. Whoops, error. Okay. And let's go back and redo these. I'm glad I'm not taking an exam. Okay? So there's a classic example. If I saw that and you just accidentally put 0.92 but did every other calculation right, I would give you 0 out of 15 points on that problem. I'm just kidding. Okay. Okay, so 0.94, here are the real values. 0. I was looking at the wrong thing. 0.851. 0.106 and 0.043. And those should all come up to 1 now. Okay, so now we have the genotype frequencies after selection, and they all should sum up to 1. Is that all we want to do? So really what we're trying to do, remember how that graph we were looking at the changes in the frequency of the favorable allele. So we now want to convert these to the frequency of the alleles, right? And how do we do that? How do we get the frequency of the big A allele? Nope. Here's this number, right? 0.851 plus half of the heterozygote, okay? So that's one thing that's one of the key things to really be able to understand is how, from genotype frequencies, how to calculate those allele frequencies from those numbers. And it's basically frequency of one of the homozygotes times half of the other of the heterozygote. Okay, so if you take that, 0.851 plus half, 0.106, what you get is 0.904. Okay. Do you want to do the other one? You can, 0.043 plus half of 0.106. But what you should get is the frequency of the A allele should equal, just to make sure I got it right, 0.096. Okay. So those are the frequencies of those 2 alleles after 1 generation of selection. Has one of them increased? Well, you'd have to go back. So 0.904 is what you ended up with, right? What'd you start with? 0.85. So you had over a 5% increase in the favorable allele after just 1 generation of selection with that kind of selection going on. Okay? So that's what you always want to go back and look at the starting allele frequencies and then after 1 generation of selection. Now what do we want to do though? So this was dominant selection, right? So all I changed, compared to the video tutorial and the handout I gave you was the fitness of the heterozygote, right? Was set to 1 in this case. In the previous one, it was a case of indominant selection, where the heterozygote had a relatively reduced fitness, or it was intermediate between the two homozygotes. Okay? So what do you want to, so this is dominant. This is incomplete. What are the values under those two, under that model that we got, that you got from the video tutorial or on the handout? Well, in this case, it's 0.913 and 0.087. So what's your take? What's the take home from this one? And where are we in that graph? Remember that graph I showed you previously? We're up at a fairly high frequency of the favorable allele, right? 0.9, up in that area, not down at the bottom. We're up in that plateauing phase. Which form of selection is resulting in a faster rate of fixation of the favorable allele? Yeah, under the incomplete dominance model, that one below. In that same exact, it went to 0.913, whereas in the dominant case, the favorable allele only went to 0.904. And what you can see, vice versa, right, is that small a allele is the disfavored allele. You can see under the dominant, right, it's not being eliminated as quickly. And so I hope what this illustrates, and you have a homework problem, right, that does this, I think with very different numbers and kind of looks at the mouse example. So what I'm trying to reinforce here is that incomplete dominance, right, where there's selection at the heterozygote will result, as you get to that higher phase, a much more rapid fixation of the favorable allele and a much slower, and a faster elimination too. Okay. So I know there are lots of steps, but kind of break that down into the various components, A, B, and C, and just kind of just through practice and things. The other thing is I give you homework, and I'll post the answers soon. I don't know if I'll get you your grades back by Thursday, but I'll post the key to the homework before the exam. The other thing is, just create your own numbers with people and try to do them together. And again, if you come up with the same answer, you probably did it right, and then if you didn't, then blame your partner. Okay. Or blame me. Okay. Okay, so that's kind of some of the things we want to try to, so that kind of tells you something about incomplete dominance. Okay. And those two models. Let's just do an iClicker here just for attendance. I'm going to give you a little thought problem to work in groups. How for extra credit? How's that sound? And this is going to be really short, like 2 minutes, because I was 5 minutes late for class. Okay. So let's do an iClicker. And just to click in, you can pick anything you want. There's no right answer or wrong answer. It's just for the attendance part. And I emailed about, 8 or 10 people that I don't see any responses on my iClicker, and there's now one unregistered iClicker. So check your email and see if you got something from me and let me know. So, and we'll try to get you in. Okay. Okay, any number, any letter, A, B, C, or D, just attendance. Is it dead? After, yeah, you can do it now. You can do it in an hour. Yeah, mine's batteries died. Yeah, that's mine. Mine are on 1 bar. Okay. Is everybody in? Want me to check the answers? Okay. Yeah, A was right. Okay. That's what everybody always picks A. Okay. Okay, here's the thought question. You can work in groups. 1 bonus point. Put on your exam. Based on that overall graph, what I want you to answer is, do you think, let me see how to phrase this. Which of these do you think is the least common in nature? And I'll narrow it down. Let's leave it to comparing, do you think dominant selection is more common in nature or recessive selection is more common in nature? And just say, yeah, I believe one of those is more common, and then I want you, and this will be the hard part, tell me why. There you go. You can work in groups. That's a hard, okay? I'll give you, and write it down, give you 3 minutes. You can work in groups. So pick one of them and then tell me why you think that's the reason.